Okay, today we're going to look at a little bit of review because we have a test coming up covering all of the information on square root functions. Let's take a peek at some of the stuff that we've looked at here in the last couple of weeks. So we kind of reviewed a little bit the idea of the quadratic function, of course, graphed a parabola, and we revisited the fact that we had not spent a lot of time looking at the inverses of parabolas because they were not actually functions. Okay, as you can see at the bottom of the screen there, it fails the vertical line test. However, if we were to only look at one of the legs of the inversed quadratic, we have what we refer to as a square root function. So we came across the equation for the parent square root function, y equals the square root of x. And as you can see in the graph there, it is positioned at the origin. Its vertex is at the origin. It proceeds up and to the right in that order. It begins mostly vertical, but it turns very quickly and turns to the horizontal. So upward and rightward. That's our parent square root function. Okay. We looked at a little bit of information about the positioning of the vertex. Okay. Now, remember the same thing it was true when we were looking at our parabolas. Okay, the idea of x minus h and then plus k, where h comma k was the positioning of the vertex. Okay, now we have talked here recently about what happens when you change the sign underneath the radical. At this point in time, when we were discussing this lesson, we weren't terribly concerned about that, but we'll come back to that here in a little bit when we get to that lesson. Okay. We also discussed the changing the coefficient of the radical itself, or changing the coefficient of the variable underneath the radical, changes the speed of the graph. Now the parent function should have a coefficient of 1 out in front of the radical. It should have a coefficient of 1 in front of the vertex underneath the radical. But as that 1 is changed in either place, if it gets to be a number larger than 1, that is going to speed the graph up and cause it to rise or fall towards infinity faster. And if it is a number that's smaller than 1, that is going to cause it to decrease its speed, so it'll move toward infinity, but not as fast as the parent function would have. And of course, keep in mind, if the coefficient appears outside of the radical as opposed to underneath the radical, the same value outside the radical will have a greater impact or a greater effect on the speed than the same value underneath the radical. And that's simply because if you got, like in this case, a whole number 3 outside the radical, if you put that same 3 underneath the radical, now it's the square root of 3. That's a smaller number. Okay, so we looked at a couple of examples, okay, and then we moved on. Okay, we went into graphing. Okay, now our basic strategy for graphing, okay, and this is, as some of you have learned here or kind of rediscovered in recent days, sometimes the plotting method is the most convenient safety blanket that we have as far as graphing. Some of us have gotten very, very good at reading the equations, and as a result, we're very comfortable with reading the equation and transferring plots to the graph. However, if you are not real sure about what's going on with a graph, then one of the things that you can do is you can position a vertex in the graph, ask yourself what direction the square root function will be moving from that vertex, and then you can pick some points in order to determine what the corresponding value in the ordered pair would be. Okay, so in this case, I didn't really consider I considered the vertex, but not really which direction the graph was going. As a result, you can see we ended up with some imaginary values because that was looking for the graph in a place where the graph did not exist. Now that we know more about this parent function and more about the other functions that go along with it, we would know that looking on the negative x-axis is not a useful thing. We would know it begins at the origin and it goes towards the right, so we would have only looked at positive x values. Okay, but again, then you are able to transfer that information to the graph, okay, and you can move on. Okay, again, knowing what we know now, on this equation, we probably would not look at all these values that we have in this table right now. We would look at this graph and say it has a vertex at -2, -4, and it proceeds to the right from there. So there's really no reason to look at -4 or -3 because those are going to be imaginary values. They're not actually in the graph. Okay, so knowing now what we did not know then, we can be a little bit more efficient with the values that we are picking to plug in so we can get an accurate graph. Okay. The rest of this was examples. And then we kind of reversed the process and said, okay, we've been using the equations to figure out what the graphs would look like. Now let's see if we can look at some of the points and figure out from that what the graph or the equation should be saying. Okay, so now there was kind of a procedure of several questions and thoughts and processes that we went through in order to get this done. So you might want to spend a little bit of time, maybe go back and watch this video again and make sure that you got it. This is also what we spent some time on the activity that we did in class for a couple of days. So hopefully you're better at this than you once were. Okay, but anyway, okay, several questions we would ask. Okay. Compare it to the parent function. That is a typical mainstay. If you want to know what this graph is doing, then you probably better know what it is doing differently. Okay, so one of our basic strategies is to get the parent function into the graph and then go, okay, how is this function different from the parent function? Well, obviously we have a few things that are different. Some direction changes are different. Some speed is different, stuff like that. Okay, so that's what we did. Parent function moving up. This function was moving down. That's going to cause a change in the y value. Okay, we got some height differences. How are the heights different? We'll compare the parent function to this new function and see if you can tell if there is a multiplier at work, okay, between the parent function and your new function. Okay, and then look for the similarities, okay, things that do not need to be changed. In this particular case, both the graphs are moving to the right. That means the x value is unchanged. Both of the functions begin from the same vertex, so the vertex is unchanged. So based upon the answers to these yes or no questions, we ought to be able to assemble an equation that can accompany our function. Okay, the rest of this was more of the same stuff. Again, compare it to the parent function. Compare how the directions are different. Compare how the vertex is different. Compare the speed. See if it's changed or not. Okay. Compare your other direction. In this case, they're going the same direction, same vertex. We can assemble an equation from that. Okay. Okay, the next thing that we looked at were different representations of the square root function, which was nothing more than just a different way that some of the problems can be thrown at us. Okay, so we saw, again, tabular type versions where we have X, Y, T charts and stuff like that. See if I can get through this problem. Okay, and we saw that things can be presented to us in a lot of different ways. Here's an example of a mapping. Mapping, of course, has two different sets. Typically, the domain and the range. Doesn't have to be domain and range, but this is a normal way that it's used. And arrows direct us from one table to the other, or one set of values to the other. Okay, it could be in stated form, as this problem was. Okay, but it does not change anything. It's the same set of questions, same set of thought processes to get through the problems. Okay, so nothing new really happened on that day. One of the things that we did do is we came back and said, you know what, we weren't exactly thinking about something correctly, and it was something that we had kind of deliberately ignored, and it dealt with the variable that was caught underneath the square root. Okay, now depending on whether you're looking at the regular function or the inverse function, it might be the x for the regular function, it might be the y for the inverse function. But regardless, whatever variable is caught underneath the square root, if you reverse its sign, we discovered that not only does it reverse the direction of the graph with respect to that axis, but it also was inadvertently moving the vertex. And in order to combat that problem, what we had to do is we had to reverse the sign of the vertex when we are identifying it. So if we have a need to pull the vertex out of the equation, okay, we're still kind of thinking along the lines of that typical formula that you're looking at there in the top third, the x minus h plus k. Okay, still pulling that guy out of underneath the radical, understanding that that's supposed to be a minus between the x and the h. However, if we have an axis reversal also going on with that variable, that's going to cause us to have to change the h sign back. Or if it's a y underneath the radical, then we're going to have to change the k sign in order to get the vertex positioned correctly. Okay, so that's basically all the new information that was on this one. We just looked at some examples of how those work. So watch that video if you're still struggling with that. And then the final thing that we did was on inequalities, dealing with the square root function. Okay, well, nothing new with inequalities, of course. Just remember that an inequality opens up the possibility that not only points that are on a line or curve are solutions for that equation or inequality, but with an inequality, points in open space are also going to yield true statements to go along with the inequality. Okay, so we talked about kind of dealing with the inequalities, and okay, we looked at when our variable is isolated. It's typically a very easy thing to read as far as the shading of the graph. If the equation says x is smaller than the graph, well, the smaller values of x are off to the left. You shade from the graph straight left. If it says x is greater than the equation, then, or the inequality, then you shade straight to the right. If y is less than, then you shade straight down, and if y is greater than, you shade straight up. So not a big deal to do with that. Okay, we talked about if the variable is not isolated, that is always a strategy. You can isolate the variable and try to do that. However, if your math skills are not all that good and you have a habit of making mistakes, whether they're silly mistakes or legitimate mistakes, whatever, okay, you might want to use the test point method. Okay, and you can plug into the equation and then judge for yourself. Does the equation lean the direction that the inequality says it should or not? Okay, because if it agrees with the inequality, then you ought to shade toward the point that you picked. If it does not agree, you should shade away from the point that you picked. And if you happen to end up with an imaginary value, then you pick a better point and try that one instead. Now, the only thing that we really said was dealing with the math of an inequality is, of course, keep in mind in the graph, you have two different ways of drawing your graphs for an inequality. We have solid lines and we have dashed lines. The solid lines are for the equal inequalities, such as less than or equal to, greater than or equal to, and they get solid lines because those are actually parts of the solution. They are included as our answer. However, we put a dashed line for the non-equal inequalities. That would be less than or greater than. And we make them dashed because they are the boundary for the shaded area, but they are not considered to be part of the solution, meaning any point that actually exists on that curve is not actually going to satisfy that curve, so it would not be a good answer. And of course, keep in mind the only new math that goes along with anything that we did as far as the numerical aspect of it is dealing with an inequality. If you are trying to solve for a variable, remember, if you multiply or divide the equation or the inequality by a negative value, then that is going to reverse the direction of the inequality. So if it was pointing one way, and you multiply or divide by a negative number, it is now going to point the other direction. You absolutely must do that. If you do not, it will cause you to shade the wrong direction in your graph every single time. So that's basically your review. Hopefully that'll help. I'll post this on Edmodo for anybody that feels like going back and listening to it again. Be sure to study hard for your test. Make sure you know how to work the problems on the worksheets that you have already had. I don't give you new assignments because all I want you to be able to do is to work the assignments that you've already got.